First, the nature of molecular bonds are not as taught in the last century of textbooks. The electrons are not in orbitals, Bohr's angular momentum model. How? The electrons are also not probabilities. They are particles with physical position. So, the basic atomic structure electrons in a duopole structure at the Bohr radius. Electrons get both pushed and pulled relative to the nucleus. The pull is electrostatic force, opposites attract. That is the red line in the graphic. However, like being Newtonian opposite inside the nucleus keeping protons together, the strong nuclear force is the Newtonian opposite for the electrons versus nucleons. I call strong nuclear force as the direct nucleostatic magnetics because its profile is 1 over distance cubed. That is the profile of magnetism. That is the blue line in the graphic. In combination, the net 2 force is the green line. This is a self-sustaining equilibrium. The 2 force are equal, and in opposite direction at the Bohr radius. So, electron never fall into the nucleus. The electrons are in a structure around the nucleus averaging the Bohr radius, with an adjustment for Pauli on the next slide. The wording of nuclear force means that the strength disappears beyond the atomic range. Look at the graphic. The blue line goes to 0. The green net 2 force line at 3 times the Bohr radius is indistinguishable. Equipment cannot find a variance from must electrostatic beyond 3x the Bohr radius. That is the nature of 1 over distance cubed. It gets smaller exponentially faster. Yet, the amazing thing is the ratio reverses inside the Bohr radius. At less than 1, the 1 over distance cubed is actually larger than electrostatic. That is subatomic behavior is not electrostatic, but almost entirely magnetic. Strong nuclear force is repulsive, so it pushes back to keep the electrons in the shell. Yet, that balance is a downslope through 0. So, if closer, the electron gets physics positive repulsion. Back to Bohr. If further away, electrostatic attraction is bigger, pulling the electron back to Bohr. So, there is a classical, Newtonian net 2 force calculation for electron to stay in shells, and electrons to take certain positions. Electrons are attracted to a net 2 force positions relative the nucleus and is nucleostatic magnetics axis. Remember this strong nuclear force is magnet-like which leads to Pauli. We have all heard of Pauli pairs. We know that the periodic table is built by nature with each of the rows as multiples of 2. There are thousands of calculations where this preference for 2 occurs in chemistry and physics. That is because of the nature of magnetics. That is, that magnets have 2 poles. Now, let's look at the graphic. 2 electrons want to be as far away from each other as possible. Yet, those 2 electrons are still net 2 force attracted to the nucleus up to the Bohr radius. Every time there are 2 electrons they want to take these 180-degree positions. That math is basic 3D engineering. So, their physical reason for Pauli pairs. It is not abstract, but the mechanics of free particles, forces and magnets. So, now I will apply that 3D engineering to the bonding of one atom to another. Notices that this model has no orbitals. It does not use hybridization of electron probabilities. Instead, electrons are attracted to a net 2 force positions relative the nucleus and is nucleostatic magnetics axis. That is the left side of the graphic. There is a nucleus with various electrons. These electrons are shown as purple spheres. Yet, bonding is about 2 atoms which both have a set of surrounding electrons. In noble gases, those electron shells might get close, but then you have electron-electron electrostatic repulsion. Remember that like kind repel. Noble gases cannot get a bond because the electrons repel each other. Therefore, the nature of a bond is that one of those electron in a second atom is missing. It has a negative valence. That is 3D position where the outer electron of one atom can find a position attracting to the second nucleus. That attraction can be large enough to become permanent. Remember that the outer electron-electron repulsions are only a 1-to-1 ratio. The nucleus attraction is 10 or more, as in the graphic, 21 protons attracting 1 electron. In that way, that attraction can exceed the E to E repulsions to create the permanent net attractive force between two atoms. 1 electron holds the bond. That is a variance from your textbooks say that bonding is a pair of electrons. That other electron is way over in the other hemisphere at 180 degrees. It is not material to the bond strength calculation. In fact, the calculation of that attraction versus the surrounding E to E repulsions has a table. It is called electronegativity. A physics negative force is attractive, accelerating the object's closures, so less distance. Hence, the minus sign. Let's review that graphic more for a standard bond. There is an electron shown as a purple sphere. It is in the atom with other particles to the left. However, it is attracted to a second nucleus by the large 21 count. That is the blue arrow. However, that is offset by E to E electrostatic repulsions. Those are the red arrows. Yet, I have added another part. Those E to E repulsions are at the side. So, that provides sideways forces to keep that electron at a bonding angle relative to the atom's nucleostatic magnetics axis. That is shown as the yellow arrow. In total, this provides a 3D engineering system for A, covalent molecular bonding, at B, noble electronegative strength, also at C, noble angles relative to the nucleus axis and to other bonds. The graphic here is from Arno's Scrunched Cube 3D Engineering Tools for SolidWorks, a program to create both engineering and animation. This is not an orbit. The electron and proton have preferred positions. The second position at 180 degrees is where hydrogen bond occurs. I think of a hydrogen atom then as based upon the magnetic duopole. That is, shell 1 nuclei have 2 positions for electrons to settle. 2. Then shell 1 is full. Hydrogen, then helium. However, hydrogen is not complete. So, 1 position is contributing, and the second position is receiving. That is the nature of the hydrogen bond. Whenever a molecule has a contributing hydrogen, there is also that second bonding position that most people forget. They get happy with their filling of the 8, but shell 1 is not 8. In the graphic, the nucleus is shown as a gray ring. Another video explains why that is appropriate, but not here. Each electrons gets shown as a blue sphere. First position to the upper right is contributing. That has a red spring because there is some flexibility in the 3D engineering program. The second position gets the receiver position. That is shown as a blue connector. Now, remember that both sides each want the spacing of the Bohr radius, so there is not collapse. Both sides operate based upon the net 2 force. With that basic understanding, users can engineering any hydrogen bond. It will generate extra bonding positions at 180 degrees from every contributing hydrogen in a molecule. In fact, that extra position is a huge part of stickiness. Those contributing hydrogens in cholesterol makes it sticky in arteries. Those contributing hydrogen in H2O, known as water, cause the high boiling points. Let's explore that more. In a hydrogen bond, you have the contributing hydrogen with electron inward and proton outward. That provide a range of at least 1 Bohr to the contributing bonding electron, a second Bohr radius to the hydrogen proton nucleus. Then there is another Bohr radius to the second atom's outer electron, and then the spacing of that electron to its nucleus. This is a long, 4-part chain. Please note that the hydrogen section does not, and that is very important, have those surrounding electrons. This creates the 2 main features of hydrogen bonds. First, the proton outward has no other electrons for repulsions, so I will attract more than another atom. That makes hydrogen bonds the most reactive. A free proton will grab some outer electron, and that often starts a chemical reactions. However, the second physical feature is that the lack of surrounding electrons provides zero stability. So, these bonds are very, very easily broken. So, What is a hydrogen bond, the strongest or the weakest? Well, it is both. It is strong because it grabs molecules the best in the short time frame, but it is weak over the long time frame because any side force will disrupt that four-part chain. Electrons have settling positions in the nucleus frame of reference. Again, this is different from the last century of textbooks. Yes, electrons can move around. There are not iron bars holding them together. They are free particle, but that is a very small range. It is a 3D pendulum of say 10 diameters of the particle. That is like a person having 10 meter space at the bottom of a 10,000 meter deep well. You can move around, but you certainly cannot climb out. Particles get pushed and pulled until they find this lowest energy positions with the net 2 force towards the nucleus offset by lots of repulsions from the side. That is very important. It gets to the biggest factor in understanding hydrogen bonds. The electron is pointing inward at the negative valence position in the second atom. The hydrogen proton, that huge positive electrostatic charge, has settled outward. Any molecule with those negative electrons is attracted to attached at that proton outward position. That is what makes hydrogen very sticky. For example, in H2O, called water, that means that at the two positions, the hydrogen nucleus proton has the second positions ready to bond at the additional position. With 6 positions with electrons, the H2O can easily stick. In the graphic, the golden ring is the outward hydrogen proton nucleus. I use this graphic often to help people understand how orbits were understood. You see, Rutherford had an experiment, and a time-lapse photograph, that showed electrons all in a circle. I understand the picture looks circular. However, what that orbit model misses is that the gas state is the entire structure rotating, so yes, the electron goes in a circular path, but in the frame of reference of the nucleus, the electron is fixed, attracted, and locked in place. The gas state is about having so much rotational energy, that a bond can never form. And a hydrogen, with that proton outward, does 2 things. 1, it raises the energy, the boiling point, needed because with proton outward more temporary, hence liquid, bonds will occur even with more energy. The electron-electron interaction closes up bonding positions with enough heat, as rotational energy. Further, that means that hydrogen bonds also change the closed container ideal gas law calculation. It is not all electrons outward, so hydrogen bonds do not follow PV equals nRT. It is 3D engineering that causes the abstract exceptions in the last century exceptions. It is 3D engineering that causes the solid, liquid, and gas states of matter. It is 3D engineering that causes bonding distances and bonding angles. Let me repeat that for emphasis: a molecule with a hydrogen, with that proton outward, does 2 things. 1, it raises the energy, the boiling point, needed because with proton outward more temporary, hence liquid, bonds will occur even with more energy. The electron-electron interaction closes up bonding positions with enough heat, as rotational energy. Further, that means that hydrogen bonds also change the closed container ideal gas law calculation. It is not all electrons outward, so hydrogen bonds do not follow PV equals nRT. So, hydrogen bonds are the mostly based upon fact that shell 1 has 2 bonding positions, and hydrogen has only 1 electron position filled. So, any molecule with contributing hydrogen has a second position receiving at 180 degrees. That creates a powerful combination. Hydrogen bonds have very high strength to occur, yet very, very weak sideway bond strength to stay. That is, very sticky, but not permanent. Further, that outward proton is ready to bond to anything nearby. This makes the hydrogen bond molecules great as enzymes to break other bonds. That proton outward pulls other molecules apart in the correct conditions. Finally, in H2O, that enzyme reaction gets enhanced. The ratio of hydrogen, and thereby hydrogen, bonds, Changes with the pH changes to all protons outward. That is, you can have a hydrogen bond reaction machine with low pH solutions. Those proton outwards bump into any molecule and any bond not very strong gets pulled apart. Hydrogen bonds will be a very important part of all of chemical engineering.